Indeed, this is my fourth time here. I don't know why I keep getting invited back. I think each year the talks get more technical and less accessible. So maybe I'll continue that trend, and then until I don't get invited back. Let's see if this thing works. Does this work? No? Aha, very good. Oh no, the punchline. So this month actually marks it's been now over 10 years since I started down the crazy path, the rabbit hole of building what are now called data science tools. They weren't called that back then. Maybe I shouldn't have had a beer. So I started writing the lines of code that became the Pandas project in April 2008, and it's been kind of a wild ride since then. I handed over the reins of the project to Jeff Reback and the other maintainers in 2013, and they've been doing a great job the last 5 years, keeping the project growing and healthy, and that continues to the present day. I've gotten involved in some other open source projects in the Apache Software Foundation, started a couple of other small projects, wrote a book, did a second edition. I had a startup, so it's been an interesting ride. I'm still here. I'm still building data science tools, so I haven't been thrown off the train quite yet. But I've spent a lot of time thinking about now with the perspective of looking at the last 10 years and how far we've come with open source data science tools. And if you look at my talks here at the R conference the last 2 or 3 years, I've been spending a lot of time thinking about where are we going over the next 10 years, over the next 20 years, and how can we plan and work together to build a better future for ourselves. And so I wrote a talk at the end of 2013. I gave it at PyData NYC, and the title of the talk was 10 Things I Hate About Pandas. And so as we've been building the software, you know about all of the things that are not good, and so I've tried to kind of distill all of that learning and complaints and grievances and turn it into something productive and maybe build some useful software that can put us on a better trajectory to build better data science tools in the future. So one step that I've just taken this year is I've founded an organization called Ursa Labs. Hopefully the reason behind the name should be obvious. But in general, funding open source software is very complicated, and it's tough because people struggle with giving money to fund open source developers. So I think there's, like many people, they download the software, they use it, but they don't think a lot about how is that software produced, like who are the people that are producing it, and it has been incredibly difficult for individuals who are building projects to obtain full-time, no strings attached support for building the projects that they're most passionate about. And I personally have been through several iterations of different approaches to obtaining sustainable funding to work on my projects, including Pandas. And Pandas was primarily self-funded. It came out of money out of my own pocket and money that I could have been making doing consulting or working in here in New York in a financial firm. So I'd be much wealthier if I did not work on open source software, but I just felt it was the right thing to do, and I was willing to make that sacrifice. I've done some other things. I've done consulting supported open source development. I did found a venture-backed startup with the intent of funneling R&D time back into the open source ecosystem that brought with it its own challenges and kind of difficulties that come with startups. I've worked on open source projects inside larger companies. So the last 4 years I've been with Cloudera and with 2 Sigma. So starting a lab. So I'm partnering up with RStudio to build the lab. So get to work formally with Mr. Hadley Wickham, for the first time. We've worked together informally in the past, but this will be the first time that we get to work on a project together. But the idea is that we're creating an organization to be able to raise money from companies that depend on open source data science tools, and that money will be used directly to fund salary and benefits for full-time developers who are building projects to make the whole Python, R, general data science ecosystem stronger and better. Last few years I've been building a project, helping build a project called Apache Aero. So a lot of this work will be based on Aero for some reasons that I will talk about over the next 15 minutes. And the goal is to create software that is portable and promotes collaboration and software use across the data science world, so that we aren't simply solving problems that R programmers have or that Python programmers have, that we're creating reusable software that can benefit the entire open source data science world. And I think that as time goes on, it will get easier and easier for that collaboration to happen. So I'm the director of the lab. Hadley is advising and making sure that I make fewer mistakes and that the needs of the R community are looked after, and we are going to work together to, because really, if you look at what Hadley and I do, we think about the human interface with data. And so a lot of people thought, oh, well, Hadley and I are, we should be enemies because we build Python and R tools. But really, what we do is we look at how data scientists work, and we want to make their lives better. It's like, how can we make the individual more productive, able to spend more time thinking about data science and solving problems, less time thinking about code. So if we can translate our ideas about working with data into code that is easy to reason about and easy to write, that makes the whole world more productive and more effective. And so over the years, he and I have bonded over our kind of passion for making people more productive working with data. And so I think collaborating on these projects will, the whole will be greater than the sum of its parts for sure. So the last couple of years, I've been with 2 Sigma, so they're sponsoring and helping support this work. Our studio is taking on the administrative burden of operating the lab. So when I hire people into the lab, they will make that a lot easier on me, so that I do not have to spend all my time running a company. And we are going to be fundraising and looking for more sponsors and development partners to get involved. So if you have a budget for sponsoring open source and would be interested in getting involved, please get in touch. We'd love to hear from you. So now let's get into some slightly more technical matter. So my talks here the last 2 New York R conferences have been about Aero. It started out like, here's a project that just started. Here's some pie in the sky ideas that we're really excited about. Last year it was, hey, we've made some progress on those ideas, and now we've made a lot more progress, and so things are starting to get really, really exciting. So I think a year from now, if I'm invited back, I'll have more and more to tell about what's going on. But the idea of the project is that I identified in my work on Pandas a lot of problems that I was running into around, how do I share data with this data processing system, or why am I having to reinvent the wheel to read CSV files and to read data out of databases efficiently? And so kind of if you look at the Pandas project, it's this whole world unto itself where we've had to solve all of these data access, data manipulation, computational problems for ourselves. We aren't able to take code from the R world and reuse it, or code from the Java world and reuse it. And so I kind of drilled down and said, how can we build some technology that can enable us to share data and share algorithms more easily? So while I was at Cloudera, I spent about a year trying to get folks together, kind of get a band together to build a project to see if other people agreed that this was a problem. Luckily, they did, and we were able to get together 25 or 30 open source developers to create the Aero project, and we've been growing the team since then. So one of the biggest, kind of most important use cases for Apache Aero is, what I call defragmenting data access. So if you think about the problem where you've got all of these computational systems, all of these data storage formats, data access, points of contact for data access. So there's a lot of energy loss dealing with, like, how do I get data from point A to point B? How do I convert between one system's memory representation and another system's memory representation? And so legacy systems still may use a native memory representation that is not Aero, but they can retrofit themselves to be able to support Aero export and import, and that will make things a lot simpler for systems that want to plug in that also speak Aero. And as time goes on, when new data processing engines are developed, we expect and hope that systems will choose Aero as their native format for analytics in memory. So I think of this as the portable data frame problem. So we say data frame, like R data frame, Pandas data frame, Julia data frame. But if you drill down below just the language into the technical details of, like, when I say data frame, like, what actually is that thing? If you look in the DRAM in your computer, how is that memory arranged in virtual address space? And an R data frame at that level is completely different from a Pandas data frame. It's completely different from a Spark data frame, and so forth. So the idea of Aero is to define a language-independent data frame representation that is suitably general to address 99% of use cases for data frame like tools, and to have native implementations across the gamut of programming languages that are used to build data science tools. So if we're in the Python R ecosystem, we can write code in C, C++. If you're in a different ecosystem, you might be writing code in Java or Rust or Go or JavaScript. So Aero is not specific to any programming language. So there's some major use cases where the project is getting picked up in the world. So one is as a primary runtime memory format for analytics. So when you load data from files or you pull data out of databases to do some data manipulations or perform some analytics, the data is arranged in memory in Aero format. And so then you run your algorithms on the Aero memory. And what's exciting about having this runtime format is that if I have an algorithm that knows how to process Aero memory, that algorithm is automatically reusable. So it's very difficult right now. If I write an algorithm that processes a Pandas data frame, I can't take that code and process an R data frame because the memory is different. Using the same technology, we've been developing tools to enable data to be shared between processes without copying. So this is about making it really cheap and easy to access very large data sets and to blur the boundary between data in memory and data on disk. So if you have a really huge data set that is on your laptop in a solid state drive, maybe it's a terabyte of data, or maybe it's 100 gigabytes of data, maybe there's only a small chunk of that data that you want to use for your analysis. With a lot of data serialization tools, in order to access that subset of data for your analysis, you have to read the whole data set. So if it might be like the middle of a CSV file, so you have to parse the whole CSV file before you can get that middle chunk. So Aero makes that problem go away, where you can just access only the data that you need, and you can get access to that very cheaply. We've been using Aero to build file formats. So you may have heard of this thing called Feather that Hadley and I made. So that was a first example of building a file format that uses Aero, and I think that we'll see more of that sort of thing develop in the next couple of years. And so I know in the R world there's another competing file format with Feather called FST. And so the way I would describe FST is as an evolved version of Feather that can only be read in R. And so from my point of view, like, having file formats that can be read in any programming language is that's really what I would like to see. One of the biggest, the project has grown so much, it's no longer just about data frames and columnar data, but the columnar data format is one of the biggest parts of the project, where we spent the most time designing a suitably general and efficient data frame representation for analytics. So I won't go through these details, but these are things you can read more about. We've been building libraries in many programming languages. So we started out with Java and C++. We now have a native JavaScript implementation. It's really cool. You can generate an Aero file in Java or Python and send it to the browser and read it without doing any parsing, so it doesn't go through JSON or any of that, and that's really neat. We just received a donation of a Go implementation, which was created by Influx Data, which builds InfluxDB. I need to update this diagram because we have a burgeoning Rust, native Rust implementation, which is really cool. I know there's also a Julia implementation somewhere in the ether that I hope can get merged into the Apache project. And we've been building bindings, so I've been working on with many other people on Python bindings. There's also Ruby bindings, which are kind of like Inception, where it's like bindings on bindings. So Ruby is going through C, which is talking to C++. So it's you have bindings to bindings to bindings. Starting to see Aero used in some pretty cool applications. So if you follow work happening in the Berkeley RISE lab, which is oriented around real-time secure machine learning, they've developed a machine learning framework called Ray, which uses, they developed a shared memory object store for managing data that flows between tasks in a reinforcement learning setting. And so that object store is called Plasma, and they donated that to the Aero project, and it's become a tightly integrated component so that we can see more machine learning systems built on top of the mantra of free data access and shared memory, which these libraries make so, much simpler than doing it by hand. Many companies in industry have been contributing to the project, so I won't go through all of them. So it's really great to see some bigger companies, like folks from Intel and HP, and so I've been contributing through Two Sigma, and of course I was at Cloudera before that. But this is we're getting a lot of inbound interest, and I think over the course of this year and next year, I think we'll see a major uptick in kind of investment from the big tech companies who want to support kind of Aero in their systems. We're up to 140 contributors on GitHub. This is our kind of Jira burn down chart. It turns out that not everyone uses Jira, but you can see that we kind of got off to a slow start, and then there was an inflection point at the end of middle of last year, and so it's been kind of to the moon since then, and I think that trend will continue over the next couple of years. We've made 9 major releases, so I'm not going to bore you with the details of what these releases, but just want to give you a flavor of what's coming in the project and how it's relevant to data science users. So let's talk about computational libraries, because at the end of the day, what this is about for data science users is making data access a great deal faster and more efficient, making it easier to use multiple programming languages. So if you want to use Python and R together, this technology makes that much simpler. And so I don't know if you saw the Reticulate package from RStudio, which provides Python integration in R. So having kind of Aero support to be able to move data between Python and R will make that whole stack a great deal more powerful. So at a high level, the way I think about the problem, having worked in this ecosystem for a long time, is that Python and R are built on this computational foundation that was established in the mid-1990s, where looking backward from, say, 1995, everyone was programming in Fortran, and it was, you said, hey, wouldn't it be great if we had interpreted programming languages that could manipulate the same code, the same linear algebra libraries, multi-dimensional arrays that we're using in Fortran, but we could do so in an interactive, interpreted environment. So hence, we had NumPy develop in Python and equivalent types of tools in R. But there's a lot of problems with the computational systems that perform analytics in memory. So a lot of the algorithms are single-threaded. There isn't a great deal of, the execution model, the way that algorithms are evaluated is very much, one step at a time. There's a lot of temporary data that's produced. So there's a bunch of problems there. And what's happening is that you look in the Python and R ecosystem, and people are if your data is small, everything's fine. And so it turns out that a lot of people have small data, and this is just not an issue. But as soon as you start getting into the tens or hundreds of gigabytes of data, you start to get into strugglesville. And so, I've been there. And really, you think about where things are going. We've got these machines with tons of RAM, tons of very fast solid-state drives, and lots of cores. We should be able to work with 100 gigabyte data sets on a laptop without even thinking twice about it. And so that's the world that I'd like to get to. So to have as many of our algorithms be multi-core, GPU accelerated. We have all this fancy code generation stuff that we can employ to make things even faster. There's a lot of sophistication that we can bring to the table, and a lot of this comes directly out of the analytic database world. So it's not like we even have to reinvent wheels. We just look at what the database world is doing, and we adapt those ideas for data science use cases. So there's a wealth of literature and learning that we can bring to the everyday lives of data scientists. So. So a lot of the work, I'm running out of time, but a lot of the work of the next couple of years will be building computational libraries that process the Aero memory format. So these will be native code libraries that create shared libraries, C, C++ shared libraries, so we can use them in Python, we can use them in R, we can use them in Java through JNI bindings. I think we'll see computational libraries built in Rust and other languages, and so those could also be brought to the table. So all of this will be portable code that can be used in any programming language. There's plenty of other stuff we got to do. We got to read CSV files. Everyone loves to read CSV files, but it has to happen because it's really important. But my goal in the long run, and where I hope we see ourselves in a decade, is that we have portable, high quality, high performance libraries that we can develop the front end that suits us, whether that's an R front end or a Python front end, and we have the same quality of experience and performance and scalability, regardless of what programming language we're using. So that's all. I'm sorry for running over time, but with Ursa Labs, I will have a lot more time and more leverage to work on these problems. So that's super exciting. I have about like a 15-page tech vision document that you can read all about this stuff. So I've been thinking about these problems for a really long time. So maybe you'll have some ideas, and I'd love to hear from you. And if you'd like to get involved in the development, the best way is to get involved in the Apache Aero project, which is on GitHub, and we're there to help, and we'd love to have you involved. It is systems work, so it's it's a lot lower level than a lot of the work that the data scientists experience day to day. But I found that I quite like the systems work, so that's good. Thank you all.
So